All right, good afternoon, everyone. So we're going to continue our discussion about classification. So we're starting with binary classification.
The screen is not on.
Oh, I'm sorry. Okay, here we go. So we're starting our discussion of binary classification, and in binary classification, we have training data of XY pairs, just as before. XI has D features, but now the targets YI are going to be binary. So typically we're going to think about 1 and minus 1 or 0 and 1. It doesn't really matter. It's just sort of a notation. It affects some of the derivations, but we'll mainly focus on 1 and minus 1. And our objective is to design a classifier. We'll call it f of x. So that takes in test feature vector and produces an estimate of the true y that has to be either 1 or minus 1 because those are the only valid values. And so sometimes it's going to get it correct, in which case we'll have the perfect value of y as in the test target, and sometimes we'll be wrong. And so our objective is for y hat to equal the true y with high probability. So one thing we can do differently now than we did with linear regression is, since the classifier only outputs one of two values, we can draw plots like this where we have one of the features on one axis and the other feature on the other axis. And now we have what's called the decision region. And when you're on one side of this decision region, the classifier is outputting one value, and on the other side, it's outputting the other value. So this is going to be how we typically visualize classification. Okay, and we're focusing on linear classifiers. So in general, this boundary can be nonlinear, but we're focusing on a special class of simple classifiers, linear ones, where the boundary is going to be linear. So it's going to be a line in 2 dimensions or a plane in higher dimensions. This linear classification procedure works in 2 stages. The first stage looks exactly like linear regression from previous units that we've studied. We changed the notation. Instead of betas, we're using B and W, but essentially these are just linear weights. We have our features here, and the output of this, we're calling it Z. This is a real number. This is not the final output of our model. It's what we call the score. The final output is a thresholding of that score. So when that score is 0 or positive, we're saying put out y hat is 1, and when that score is negative, we're saying put out y hat is minus 1. Okay, so the first stage looks a lot like linear regression, and the second stage is basically a form of quantization. And yeah, so we said that in this case, the model is linear both in the coefficients as well as in the features x. And when it's linear in the features x like this, when it's linear in both, it creates this linear boundary. So that linear boundary, sometimes, like in this case, that's exactly what we want. In other cases, like this, the linear boundary is not what we want because there's no way I can come up with a line that perfectly splits into green and blue. What we said is that we could maybe transform our features first using some nonlinear methods, and then in those new features, we do linear classification. And when we look in the original feature space, then the boundary becomes nonlinear. In the transform feature space, it would be linear. Okay, so this is a trick we can use to expand the power of this idea, which on its own, applied to raw features, is pretty limited. But if we allow transformations of features, then it becomes powerful enough. Okay, so that's linear classification. And then the next big question was, how do we fit the coefficients in our model? So we have this intercept, and we have the slope coefficients, W. And we said, what if we just used least squares fitting, where we plug in for the targets the binary training labels? And so we know exactly how to do this from previous units, but what we found is that in some cases it seems to work well, but in other cases when the data is somehow imbalanced, like when you have features that are spread out more on one side of the decision boundary than the other, then the performance of this falls apart. And so the moral of the story is that this RSS cost function is not going to work for us now that we're doing classification. We need to think about something else. So we said, what about this idea? Let's come up with a probabilistic model that essentially treats y as a random variable, y is the label, given a particular value of z. And the simplest of this class of models uses this, this ratio here, e to the power z over 1 plus e to the power z. If you plot it, plot this probability as a function of z, you get this sigmoid shape. So when z equals 0, which we know is on the boundary right on our decision region, you find that this gives you probability of y being 1 of 1/2. Probability that y is not 1, that is also 1/2, so that makes sense. That's the point where we just have no idea what y is. It's equally probable to be 1 or minus 1. But as z gets more positive, we gain more and more confidence that the label should be 1. As z gets more negative, we gain more and more confidence that y should not be 1, and that instead should be the alternative, which in this case is minus 1. So this is basically what we call the logistic model. This is the most popular one, but it's not the only one used for classification, and we'll see some other ones in future units. Okay, so then the question is, well, okay, great, we have this model. How exactly how do we turn this model into some procedure where we can design the weights, the coefficients? And what we said is we can just use maximum likelihood estimation, which we learned at the end of the last unit. And the way that this works is we write the probability of all the training targets given all the training features and the parameters of our model. And we then basically turn the crank in this procedure. So the first step is we assume that all of these XY pairs were generated independently. So that allows us to factor that joint probability into a product of these marginal probabilities. Then for derivation simplicity, we tend to take the negative log of this likelihood. That turns this product into a sum of the logs of these terms. And now we run into kind of an inconvenience for logistic regression, is that we don't have a single expression for this that holds for the two values of y. In fact, if y is 1, we have one expression, and if y is minus 1, we have a different expression. So the way that we tackled that is we said, let's put in some specially crafted, what I called switching variables, so that when y is 1, the first of these variables turns on and puts this in the model. This one turns off and kills this. So whenever y equals 1, we now can we know what to plug in here, and it's that expression. On the other hand, when y is minus 1, this goes to 0, but this turns to 1, and so we have this. So now, with these switching variables, we can just plug in this into here and this into here. And at that point, we just have a bit of algebra to do, which finally gives us this negative log likelihood that has this expression here. It's still a little bit complicated because this is written in terms of the zi variables, the scores for the ith training sample, and the zi's are what depend on our b and w coefficients. So we're going to learn more about the details of doing this maximum likelihood fitting in Unit 6. We're going to get into algorithms that do this, but for now, we're just going to exploit the fact that sklearn has functions that will do this optimization for us. And so we can just use those functions, and we'll talk about those in just a little bit today. Okay, so basically, so just to summarize, in this case where the labels are 1, -1, in order to fit the intercept and slope coefficients, we do a joint minimization over B and the W vector of this cost, and this cost is called the binary cross-entropy loss. If we would instead have labels 0 and 1, which is equally, if not more, popular in different textbooks and so on, then the only thing that changes is the switching variable turns into yi, and so you get a slightly different expression. So the expression you use depends on the values of the targets. Okay, so that is where we ended up last time. And are there any questions on anything so far? Okay, great. So now we can take a look at what happens on our data set. This was just a toy data set where we had 8 samples. So we had 4 samples whose feature locations were there, and they were all -1 targets. And then we had 4 more samples with these feature locations, and they were all +1 targets. And so when we do least squares linear regression, we just we look at those yi's, we try to minimize the RSS, and that gives us this regression line like this. This would be, again, our scores z as a function of the test feature x. And then we said the second stage is quantization. So whenever the score is positive, so here's the 0 line. So whenever the score is positive, which is to the right of its 0 crossing, we assign y hat is 1. Whenever that score is negative, we assign y hat is -1. And so the problem now is that because z change sign to the right of this training sample, we would actually misclassify that training sample. This least squares linear regression style training actually doesn't even allow us to fit our training data. It's getting distracted by this outlier. It's trying really hard to fit that in a least squares manner and giving up on its ability to fit this correctly. That's just the trade-off it's making for RSS, but RSS is not really what we want to do. So if we instead try this new method, logistic regression, it's more complicated, but we basically rely on some sophisticated software to minimize this to come up with our weights V and W. And it turns out that now the linear part of this two-stage method produces this line. So this is like the thing that generates our score Z. And when you look at its 0 crossing is here at the value 5. And so, so this is where, when we quantize it, we either get 1 or -1 when it's to the right or left of here. And that appears to be perfectly set up right in the middle of where our data is switching from positive to negative, even though we have this outlier that is distracting it. So it did not get distracted by this at all. It seemed to do exactly the right thing, which is to put this linear score through this point, and then therefore the decision boundary is right here. So it worked perfectly. Didn't get distracted by this point. Okay. Any questions on that? Okay, so then there's one other thing we can look at. Now that we have a probabilistic model, we know that we have this idea of the probability that y equals 1 given z. This is something that is just a simple expression like this. So now what we could do is, as we change x, we know that that changes z according to this curve. We plug that z into this expression. That gives us the red curve. The red curve is our modeling of the probability that the label is 1 as a function of x now. So you can see that right here, at the decision boundary of x equals 5, we get a probability of 0.5, which is the most uncertain, 50%, we're 50% confident that it's 1 or not 1. But then as you go to the right of the decision boundary, we get more and more confident, and eventually, by the time we're out at this outlier, we are almost perfectly confident that it is should be classified as 1. Meanwhile, as we go to the left of the decision boundary, we get more and more confident that it is not 1, that is the alternative. Okay, so this is just a visualization that we can do because we have a probabilistic model now. Okay, so that is just to conclude the idea of logistic regression. I don't know if I mentioned that clearly, but that is what this technique is called. You might say it's a little bit confusing, like it's classification, so why are we calling it regression? So it turns out that it's called regression because the first stage of this two-stage approach really looks like regression. It really looks like we are predicting, let's see, where do I want to go? I want to go here. In this first stage, this looks exactly like the kind of regression where we are predicting some kind of real valued target, right? In this case, you could say maybe we're predicting some score. And it's only in the second stage that we're doing the quantization and turning that into classification. So not all classifiers work this way. This is kind of special for this style of classifier, and that is why it has the name logistic regression. The regression is inherited from this part. It really looks like predicting a continuous valued thing, and then, but it's based on this logistic model. Okay, so that's just a little bit about the name. It's a form of classification, but it is called logistic regression. Okay, so that brings us to back here. Okay, so any questions on anything so far? Is this making sense, or is it confusing? Okay, seeing a lot of nodding. Great. Okay, so now there ends up being something kind of it's a special case that's a little bit strange. So this is the thing we just derived. This is what we call the binary cross entropy loss. This is the loss that we would be fitting to do this logistic modeling. So if you take a close look at this loss, we can look at it in two cases. So let's look at it in the case that y is 1. It turns out that in that case, so if you take a look at this quantity, imagine that I took out the 1. You can see that quantity is just zi, right? When the 1 is gone. So if I add the 1 back in there, because the log is increasing in its argument, this is a little bit greater than zi. Okay. Meanwhile, if we think about this when yi equals 1, this is exactly minus zi. So together, these guys it has to be positive. And then furthermore, as zi gets larger and larger, this term gets gigantic, right? It gets gigantic relative to 1. So when zi is large, this 1 is so insignificant, this essentially looks like zi, just a tiny bit more. And so when you draw the curve of this, in the case that y equals 1, you get something where the right side of the curve decays towards 0, asymptotically it reaches 0. Right at the boundary, okay, when zi is 0, this goes to 0, and this goes to 0, which means you have log of 2. Okay, so right at the boundary, this is z, you have log of 2. And then as you go to the left, essentially what happens is, for negative z, this starts to get really small, right? So when that's really small, this is barely different from log of 1. So, and log of 1 is 0, so this is kind of insignificant, but this one just keeps going, and you have a essentially something like just a line of slope -1. Okay. So I'm just trying to show you the shape of this curve when y equals 1. Now let's also look at the shape of this curve when yi equals 0 as a function of z. So in this case, it's simpler because we don't have this term at all, y equals 0. And so for this term here, all right, when z is positive, we know that this term gets really big. Well, actually, sorry, this term is close to z when z is big. So we have here the same zero crossing, but then it just eventually turns into a line of something close to a line of slope 1. We also know that on the left side, when zi is negative, this is really small, and this is close to 0, but a little bit greater than 0. So we have this. Okay. So roughly speaking, those are the shapes of the curves that we have in these two cases. Now, where I'm getting to is something special happens when your data is linearly separable. So when your data is linearly separable, what happens is if yi equals 1, then zi is positive, right? Because you have this decision region, decision boundary. On one side, the I equals 1 side, you will have z's greater than 0, because that when z is greater than 0, we guess y equals 1. And if yi is 0, we get zi is less than 0. Okay, so those are the two cases. When y equals 1, we have positive z's. When y equals 0, we have negative z's. So let's take a look at those curves. So we know when we have linearly separable training data, we're in the y equals 1 case, we're always to the right. And here on this other case, when y equals 0 case, we're always to the left. Z is always negative. Okay, so remember, I want to minimize this whole thing. I want to make that as small as possible. So note, what does that say about the value of z that I want to see? Do I want to see z's close to 0 or far from 0? In this case, what do I want to see for z? Far to the right, right? That's going to minimize this line. So I want z's far from 0. In this case, same thing. I want z's far from 0. The way to get z far from 0, in either case, is to make these weights really big. In fact, the bigger I make the b and the w, the bigger z gets in magnitude, the farther from 0 it gets. So if you train this loss without any regularization on it, you will find that this algorithm keeps making these weights larger and larger and larger the longer you let it run. They just converge to, they diverge. They go to infinity. Maybe some are positive infinity, some are negative infinity, but they go to infinity. So essentially that's what happened. You could say that the norm itself just goes to infinity. So that's obviously a problem. With large weights, even if they're finite and large, that's going to cause overfitting. We've seen that before. So we know that when you have overfitting because weights are too large, to counter that, we can put in ridge regularization. So here's the ridge term. And if you go through the math, you can convince yourself that when you add this here, this is strong enough for any alpha, for any positive alpha, this is strong enough to prevent these coefficients from going off to infinity. So basically, whenever you do logistic regression, you always have some sort of penalty in there to prevent things from diverging when you have perfectly separable training data. And the default in scikit-learn is to use L2 regularization like this. It starts out with some default value of alpha, which may not be optimum. So generally speaking, you want to tune that value with cross-validation. But sort of the intuition is that if you don't have highly correlated features, all you're trying to do is prevent this thing from going crazy in the case you have linearly separable data. And so you want to set alpha 2 as really small but positive. Okay. So that's kind of one intuition. The other intuition is, well, if I have really correlated features, we know ridge regression is a great thing because it prevents the weights from getting big from correlation, and that is also an option. So correlated features, maybe you want a large value of alpha, otherwise small. But in any case, the right way to do it is to set up cross-validation and tune it on a grid and see what's the best value. Okay. But if you had to just guess, a good place to start is start with a really small positive value and start from there. Okay. So that's long explanation of why we use L2 regularization as a sort of a standard thing. Okay, any questions on that? All right, so there's an alternative, as we know. We could also use L1 regularization. So here's L2, oops, here's L2, here's L1. As we know, when we use L1 regularization, it promotes sparsity in the coefficients. So here what happens is as you make alpha 1 larger, you find that these W coefficients start going to 0, exactly 0, which turns off those features. And that's a great thing if you want to do feature selection. So here again, you have the same issue. How do you tune alpha 1? You do it exactly the same way. You come up with a grid, you do cross-validation. But again, similar to how we talked about before, you have to be a little careful about how you do it. The actual coefficients that you get out of this optimization procedure here are shrunk towards 0 because of this term. So really what you do is you use this to find the W vector, and then you just figure out which coefficients are 0 valued. You turn those off, and then you refit it with regular old logistic regression like this with a very small value of alpha 2 that won't have the problem of pulling those W's close to the origin. So that's what I'm saying here, tune alpha 1, be a cross-value performance, not of this, but of feature-selected logistic regression, like this. Okay, so that's how we do it. Now it turns out that this optimization problem here is a little bit complicated to solve. It's much worse than lasso. So when you run it, you'll notice it takes the algorithm longer to solve this problem. You just have to wait a bit longer. So that can be an issue depending on the size of your data. So anyway, we basically at a high level, we start with this binary cross entropy loss, and we're going to either add L2 squared L2 or L1 regularization, depending on whether we want to, whether we have correlated features or we want to do feature selection, etc. Okay, so that concludes this slide. Are there any questions on this? Okay, great. So let's just take a look at how we do this in scikit-learn. So we, again, use the linear model library. Now, instead of linear regression or lasso, it is called logistic regression. And the main tuning parameter that we want to give it is the regularization strength, but you don't specify alpha directly. You specify its inverse through the parameter C. So C is the inverse of alpha. So what that means is when you want this alpha here to be really small, you want C to be really big. What's nice about, I think the reason why sklearn is doing the inverse is it's sort of now impossible to set this to 0. The only way to get that to 0 is for C to be infinity, and you can't tell it infinity. So, so basically, you can say make C really massive, which makes alpha really tiny, but it will always be positive. So that's just one slight difference. So here you see C is kind of a large value, 100,000. Other than that, there are a number of options like fit intercept equal true. That's something like we've seen before. Here's where you specify the penalty. You can say L2, L1. there's some other details about how many iterations do you want this iterative algorithm to run. There's a stopping tolerance. If things get small enough, it seems like things aren't changing, it will stop, and so on. We'll get more into those things in Unit 6. And one other thing we'll talk about later today is a couple different options for training the coefficients. So for now, we talked about binary. So in binary classification, there's really only one method, but once we get to more than 2 classes, there's other things to consider. Okay, so here, we instantiate this thing. Here's where we instantiate it. This is another way to do standardization. Then we fit the model. So internally, the B and W's are computed. Then we use it for prediction. And then here we can finally find the accuracy. So this is a little trick. So remember, y hat is going to be binary. Y is binary. So this is going to be a vector of zeros and ones, or trues and falses. So whenever it got the prediction right, it's true. Whenever it's false, it didn't get it right. And now if you do NumPy mean on that logical vector, it's smart enough to just count the fraction of times it was positive. And so that will give you the accuracy, what is the percentage that you correctly predicted the target label. And so in this case, for this data set, this is the breast cancer data set, we're getting almost 97% accuracy, which is good. It's not a very difficult data set. Okay, so this is how we can do logistic regression in sklearn. All right, any questions on this? Okay, so you have this demo. You can look at it more in your own time in preparation for the lab. Okay, so the main thing to talk about next is what they call multi-class classification, where you have more than 2 classes. So here's a picture of sort of a generic case where we have 2 features, feature 1, feature 2, and we have 10 different classes. And so now in this plot, they're using 10 different styles of markers for these classes, like blue squares or red diamonds or so on. And they're also showing the decision boundaries for these different classes that were created by the classifier. So as you can see, the boundaries are a lot more complicated. There's a lot more different regions now. In this case, we do have nonlinear boundaries, but not surprisingly, we are going to focus on a linear method that would give us linear boundaries, not these nonlinear ones like this. Okay, so to set up the problem in terms of the math, we have this training data, XY pairs. As before, the features are d-dimensional real numbers, but now what's different is that the labels are integers from 1 through k. This is the way that it's usually represented. Sometimes you see it from 0 to k minus 1. But we don't want to think about these labels here as ordinal, meaning like 1 is less than 2 is less than 3. You want to think of them as different categories. They're really categorical. So even though they're specified by these integers, don't get distracted by that. They're just telling you like which category it is, category 1, category 2, and so on. So that's the main thing for multi-class classification. So similar to the binary case, we want to come up with this function f that's going to return an integer from 1 through k, and we want that the y hat, what it returns, is close to the true y integer with high probability. And just as before, we can define decision regions, the set of x, such that our classifier returns k. That's what those things are there. Okay, so this kind of brings up a question that is sort of a practical question that you might face, as a machine learning engineer. If somebody gives you a data set with discrete targets, you might wonder, do I treat it as classification or do I treat it as regression? So let's say like you're predicting product ratings on Amazon or something, and the data you have are number of stars, 1, 2, 3, 4, 5. So you have two options. You can think of that as the target as ordinal. Like 1 star means they don't like it as much as 2 stars, which means they don't like it as much as 3. Or you could say, no, I actually want to think about these as 5 different classes, 5 different categories. There's the 1 star category, there's a 2 star category. So what do you think is going to work better for that kind of data? Any guesses?
Regression.
Yeah, regression, because in some sense, you can exploit the fact that there is an ordering between 1 star, 2 star, 3 star, right? In that case, you would want to use regression. You could run classification. You could do the method we're going to describe next, but it just wouldn't work as well. On the other hand, if you have data that is like just categories like cat, dog, plane, things like that, there's clearly no ordering between them. You would want to use this multi-class classification. You could pretend, you could put those cat, dog, and so on like this, and you could run linear regression, but it just wouldn't work because it's putting this ordering on the categories that doesn't actually exist. So this is a choice you have to make. And so there's problems where it's actually a little bit tricky to figure out which is the right one. So one of the guidelines you can sometimes use is you can ask yourself the question, if I returned something in between the classes, like if I returned in this Amazon case 1.5 stars, does that make sense or does it just not make sense? So like if my predictor said, I believe that for this feature vector it's 1.5 stars, I would say, yeah, that makes perfect sense in a product rating, even though maybe the user can only click 1 through 5. I know how to interpret 1.5 or 1.3 or whatever that is. But if inside I have like cat, dog, plane, and I tell you it's somewhere between cat and dog, like that doesn't even make sense. You don't know what to do with that. So that's another way to kind of sanity check whether you want to use a classifier or a regressor for a problem with discrete labels. Okay. Is that making sense? There's a homework problem for homework 5 where you have a number of things to consider, and some of them are pretty tricky. You have to think very carefully about them. But anyway, so that's basically the point of this down here. Okay, all right, any questions on classification versus regression? All right, ready to move on? Okay. So multi-class classification is, it's a complicated problem. So the first question we have is, can we somehow attack this using simpler methods like binary methods? And the answer is yes, and this is actually, in some sense, the most popular, common way to approach the problem. So there's essentially two main ways to do this. Can we tackle it using binary methods? Yes. So the first and most common approach is called the one versus rest approach. Also, sometimes people call it one versus all. Okay, and it goes like this. You end up training, if you have k classes, you end up training k different binary classifiers. And so what you do is, let's say in this problem where you have 3 classes, red, green, blue, you would essentially say, first, I'm going to train a classifier which is blue or not blue. Okay, and now I have essentially 2 classes, blue or not blue. And you can see that if I trained a linear classifier for this, it would put its boundary somewhere like where this blue line is, right? That's one classifier. Now, you go to the red. You say, is it red or not red? You would train another binary classifier. In this case, that would give you this boundary. You go through all your classes like this, so you come to the last class, green. So now it's, is it green or not green? Okay. So essentially, we can take what we developed and we can just do it exactly like this. As a result, for each of these classifiers now, for each of these k classifiers, you will have a separate score, a separate real number. And what you do at the end is you just figure out which score is the highest. So when you get a test sample, you evaluate it using the blue classifier, the red classifier, the green classifier, and whatever gives you the highest score, you say, I think it's green, if it's the green classifier that gave you that. So that's essentially how this approach works. So essentially, with k classes, you have to train k binary classifiers. Not a big deal. We can do it. it's the most common option. So that's the first of these two approaches. Is that making sense, how we're doing that? Okay, any questions on that? Okay. There is another approach. We'll see it in one case in the next unit, but not as often. It's called 1 versus 1. And you essentially do something like that, but you do it for each class pair. So in this case, you would do blue versus green. Forget about the red entirely. Blue versus green, you train a classifier for that. Then blue versus red, you train a classifier for that. Then blue versus green, or red versus green, classifier for that. So for every pair, you train a classifier. And then now so which of these two approaches is going to require training more classifiers? At least if you have, so in this case with 3 classes, they're equal. But if I have, let's say, 4 classes or more, which of these two methods? Second one, exactly. There's more pairs. So the number of pairs is going to be k times k minus 1 over 2. So that's kind of like, you could say it grows roughly k squared, whereas this one grows with k. Okay, now, the thing about the second approach, even though you have to train more classifiers, those classifiers individually have less data to work with. Because, if I'm just looking at two classes of many classes, then I don't have that much data for those 2 classes, so those classifiers are going to be much quicker to train. So there's sort of a trade-off. It's not like one approach is necessarily slower or faster than the other. It really depends on the context. And then in this last one, what you do is you look over, you end up summing the different scores trained by these classifiers in a pair. So 2 different approaches to do it. This first one is the one we will focus on. We'll just see this one appear at one point, and now you know what it is, but we're not going to really focus on that. Okay, so those are using binary methods for multi-class. Any questions on this? Okay, all right, so now let's get into a very specific approach, which we'll see is a direct generalization of logistic regression to more than 2 classes. And essentially, we'll actually kind of uncover 2 different approaches. These are multi-classes extensions of binary logistic regression based on that 1 versus rest idea, that first one. Okay, so for each of our classes, little k, going from 1 to big K, we compute this linear score, zk. And so I'm going to use an intercept that is k specific, and I'm going to use a weight vector that is k specific. Okay, so I have, for every class, I have an intercept and a vector of weights, wkj, where j goes from 1 through d. And just as we described, you can interpret that linear score as whether the feature vector is in class K or not in class K. That's the interpretation of that particular score. And we have capital K scores, so we have one for every possible class. So that's the first stage, that's the linear stage of this. The second, nonlinear stage, instead of a quantization, it's more like picking of those capital K scores the one that is the largest for this particular test sample. And whatever the index of that score is, that is the number 1 through capital K that we report. That's the class, our guess of the class that we report. Okay, so that's just direct extension of this to logistic regression, except now, okay, where does logistic regression come in? Well, that has to do with how we train these weights, right? Okay, so there's an easy way to do it, and then there's a more complicated way to do it that works better. The easy way to do it, we can just say in one line, you just split up your data into, class 1 and not 1, class 2 and not 2, and for every one of those splits, you just train binary logistic regression just like we described a few slides ago. So train k separate binary logistic regression methods. So what that means is that when you design B1 and this W1 vector, you're just designing it completely independently of all the other B's and W's. So in some sense, it's maybe not optimal because you're not designing all your weights and intercept terms together to work with each other. They're just kind of designed in isolation. So that's sort of the downside. So now there is a more sophisticated approach that is a little bit more, it tends to work better in practice, but it's a little bit, it's more complicated and it's a little bit numerically more of an effort to do the optimization. But it goes like this. So you come up with a new likelihood model or probabilistic model. And now we're saying that the probability that the label equals is from the class K, given a vector of scores, so that's this vector of scores, is e to the power z sub k over the sum of, let me write it in terms of L going from 1 through capital K of E, Z, L. Okay, so the intuition, you can get the intuition from the the numerator alone, because in some sense you can think of the denominator as just a normalization constant that you need to turn this into a PMF, because this is a PMF or a conditional PMF. This is the probability across the different label hypotheses of the target. So just to draw it, it's sort of like maybe you get something like this. So when you look at this, you'd say, okay, maybe like it's 55% from that class, 25% from this class, and so on. So it just gives you the probability over classes. So it's a very intuitive thing that we're constructing here. And the way that we're doing it is we're just exponentiating these scores, but we just need to make sure that after we do this exponentiation that everything sums up to 1. So that's what this denominator does. Okay. So this thing is called the softmax, this guy. And the word softmax is used because what happens is when one of your linear scores is much bigger than the rest, and you look at the different these different values, you'll find that one of these guys is almost exactly 1, and the rest are almost exactly 0. So it's like a soft version of the maximum function. So basically, it's like this is approximately equal to 1 for the largest coefficient and approximately equal to 0 for the rest. This thing on the right is exactly a one-hot coding of Kmax. It takes Kmax, an integer, which is like the location of the largest one of these, and it just turns that into a binary vector where there's a 1 in the position Kmax and 0s elsewhere. So that's what this is. And this is just an approximation. This is not exactly true, but the more imbalanced these different scores get, the closer this gets to being true. Okay, so this can then function as an improved model over our binary model, where we applied it individually to different splits of the data. Now we're saying let's use this for the data as a whole. Okay, so that's the idea behind multinomial logistic regression. Really, there's, again, 2 different options here. When you use scikit-learn, you tell it which of these 2 you want it to do. Generally speaking, the first one is faster, doesn't work quite as well. Second is a bit slower, works a bit better. Okay. All right, any questions on this? All right, so let's see how the derivation goes then. So again, maximum likelihood is what we're going to use. And the optimization problem that we want to solve is argmax over the hypothesized vector of intercepts, right? Now we have capital K intercepts because we have capital K different classes, categories. And we have a separate weight vector for each category. I can stack these columns together in a matrix, call it capital W, just to be more concise. And then I'm going to look at the likelihood, which is the probability of my Y vector contains all my training labels, given my X feature matrix that has all my training features, and now my parameters B vector W matrix. So we can do this. Just want to make this a tiny bit smaller. Okay, equivalently, we could do the minimization, argmin over B and W of the negative log likelihood. And not surprisingly, the math is a bit nicer for the negative log likelihood because of the exponents in the model, and so that is what we're going to use for our derivation. Okay. So the main struggle that we end up with when we try to do this derivation, it's the same struggle that we saw in the binary case, which is that we don't have a unified way of writing this for different k's, because when you change k, it actually switches in a completely different variable into this exponent. When k equals 1, I use the first z in my vector. When k equals 2, I use the second z. And so really the form of this is changing quite a bit. And so as a result, that leads to some complications. So we want to use this switching variable idea again. And you could also think about it as one-hot coding. But it goes like this. So let's say we start with the labels being integers 1 through k, but then we turn that into a one-hot coding. So that becomes this scalar y. We turn that into a binary vector yi, where I look at the value of this. Let's say that the value of this scalar yi was k, little k. Then I make a vector of zeros and ones where there's a single one in the kth entry. So whatever value this has, that's where I stick the 1 in this model. So I'm going from a scalar to a binary vector. And I'm encoding the value of that scalar as the entry in the binary vector. So that's the idea. From the switching variable perspective, whenever the ith training label is class K, these elements of this y vector, one of them is 1 and all the rest are 0. So one of them turns on and all the rest switch off. And that is what makes the derivation tractable. Okay, so it goes like this. This is the thing we want to minimize. We know that this part I can write as a product. Actually, I should have done that. Let me try to. Sorry, let me try to do that. Makes the derivation a little bit easier. Okay, so what I want to do here. Sorry about this. I want to write this here as a product, I equals 1 to n of the yi. So this is the thing we always do with maximum likelihood, where we take that joint distribution and we factor it as a product. And so now you can see that essentially you need to work on these. If I can derive an expression for this that's tractable, then all I need to do is plug it into this model, and everything is good. And in fact, we know there's another little trick here. Let's move the log to the right side. Then we have negative sum of the log likelihood. So this is the thing that we will work on below. And then when we're done, we can just plug it into this expression. Okay, so here's the negative log PYI. As we said, the difficult thing about this is as I plug in different integers here, I get an expression where things change a lot. So here what I'm going to do is I have a sum over this new dummy variable k. These are the elements in my binary vector. And so this one turns on and switches in the right one of these depending on the value of yi. So when yi takes the value, let's say L, I will switch in this thing. Okay. So that's essentially the main trick. Now that we've written it this way, this is an expression that we know. This is our softmax model from the previous page. So taking the log of that is very easy. You have log of the numerator, that just gives you zik. And then log of the denominator, it's minus log of that. There's nothing we can do to simplify it. The very last stage is, okay, we get this. That is the second term here. Turns out we can simplify the product of this and this. The reason why is that this term on the right has nothing to do with little k, which is the summing index over here. So we can just think of that as that left term times the right term. They're not coupled at all. The left term, if you think about this is just summing up the entries in this vector. There's always one non-zero no matter what, and so this sum is always just 1. So basically this thing goes away, and you just get this over here. Okay. So finally, this is the negative log PYI. We stick this into here, and we get the expression right here. This is just plugging that into that. And this is our new loss function that we want to optimize. We have now capital K different intercepts, capital K different weight vectors, all collected into these terms. This is, again, numerical thing we have to do. The nice thing about this is a convex loss. I might have forgotten to say that in the binary cross entropy loss, that's also convex, so you can solve it without any issue. It's just a matter of having the right algorithm to do it. So that's our alternate procedure. Just like before, you want to add L2 regularization to prevent the weights and intercepts from going to infinity in the case of perfectly or linearly separable data. If you want to do feature selection, you could instead add an L1 regularization to this. Both are possibilities. Both need alpha optimized with cross-validation. So optimization problems are convex and can be solved numerically. So that is starting with the softmax, doing maximum likelihood according to this derivation. We finally get to this cost function. Now it's just an optimization problem, can be solved, and now we, after solving this, we will know our coefficients of our model, and we can apply it. Okay, any questions? All right, so that the very last thing I want to say is that looking back at the scikit-learn, there is multi-class as an option, and that is where you specify which of these two training procedures you want to do. If you put multi-class equals multinomial, that jointly trains B and W according to the approach we just described in the last few pages. If you take multi-class as OVR, then it separately trains a one versus rest binary classifier for each class using binary logistic regression that we talked about several pages back. Okay, so that is really it. It's just you can try both. You can do cross validation or whatever, but it's typically the more expensive one, multinomial, works a bit better, but it runs slower. So that's all for today. Just an announcement, I'm going to be out of town tomorrow and Friday, so I unfortunately won't be able to make office hours, and so we will not have an in-person lecture here. I can't do a lecture over Zoom either. I'll be traveling, so I'm just going to upload another YouTube video so you guys can watch it on your own. We actually don't have that much more to cover in this unit, probably like a half lecture worth. So, so that will be it. So I won't see you guys until next Monday. I posted an announcement about the midterm. Hopefully you saw that. I will be posting practice materials for the midterm. If you guys have any questions on the midterm, you can ask me now, or you have a question on the midterm?
Will the homework and lab be the same next week as it is like with the midterm?
So yeah, there won't be any midterm week. I won't have any additional assignments that week. So the homework and lab and quiz for Unit 5 will not be due until a week after the midterm. So 2.5 weeks from today. So next week you can focus on just working on the midterm, studying for the midterm, and then the following week you can get back to this. Okay. Yeah, if you have any other questions, just let me know.